We'll apply the Gaussian theorem that we know already. It's applied to different cases, especially for cylindrical shape, for thin sheet, for plane conductor, one by one. Let's consider the charged conducting sphere. Suppose the sphere is having the radius capital R and the charge given to it is Q. You know the charge is enclosed on the surface only. Rather, you can say it is confined to the surface only. If we consider a Gaussian surface around it, obviously the Gaussian surface is going to be of spherical shape. Let's suppose its radius r that's greater than radius of the sphere. The area, surface area of this Gaussian sphere that we assumed right now is going to be 4 pi r square. Now, the flux as per Gaussian theorem is Q upon epsilon naught, whereas we already know it's equal to E into A. So, E 4 pi r square, that is equal to Q upon epsilon naught. You get the value of E 1 by 4 pi epsilon naught Q upon r square. But if you consider this surface just near it, it will be in place of a small r, you will replace it by capital R, and the surface will be having the electric field given by Q upon capital R square. So, Gaussian theorem is helpful in finding the electric field because of the charged sphere. Now, let us apply it to a cylindrical shape. You see, it's a charged cylinder. You might consider it to be a line charge also. It's a simple, thin, charged cylinder of length, suppose L, and its radius is, say, capital R. Charge given is plus Q. Here we would consider another cylindrical surface that's going to be obviously cylindrical type. Let's suppose that it's having the radius is small r. This Gaussian surface will include the charge that's acquired by the cylinder itself. Here again phi, this is Q upon epsilon naught as per Gaussian theorem, and it should be E into A. You know, here A represents surface area, so that way it could be E into 4 2 pi r L, that is Q upon epsilon naught. That way you get the value of E, that is 1 upon 2 pi epsilon naught into R and Q upon L. What is this Q upon L? That's known as linear density of charge, and this is represented by lambda. So, that way you get the formula lambda upon 2 pi epsilon naught R. This is the relation for electric field produced by a cylinder. You consider the point and the surface itself. In that case, again this small r will be replaced by capital R, that is radius of the cylinder. Then we would consider a plain sheet of charge. Sheet means simply a paper. You take one paper that might be considered as a very good example of plain thin sheet. That's sometimes also known as lamina. Lamina always stands for thin sheet. So, it's a sheet. What we'll do to apply Gaussian theorem, we'll consider a cylindrical surface, but that cylinder would be taken this way. You see, the cylinder will consider it's a sheet. Cylinder would be entering and coming across it this way, or you might say it is cylinder and that sheet is going across it like this. So, in that case, we'll show that cylinder coming across the sheet One portion we have shown behind by dotted line, discontinuous line, and one portion we have shown by the continuous line. You see, for the cylindrical Gaussian surface that we assume, the area vector is going to be outward always. Area vector, surface area vector is always normally outward. If this sheet, that's this way, if this sheet is having positive charge, the field will obviously be away from it. In both the sides, field would be normally outward. So what we see, both the sides E and A are parallel. So flux there, here, in both the cases, flux is going to be positive. Here also, flux is going to be positive. So total flux, because both are positive, total flux is going to be the sum of the two, phi 1 plus phi 2, that is 2A EA, and flux is again Q upon epsilon naught according to Gaussian theorem. So what remains is E to be given by Q upon A 1 upon 2 epsilon naught. What is this Q upon A? That's known as charge per unit surface area. It's also called surface density of charge. So we get the formula for electric field, sigma upon 2 epsilon naught. Very important characteristic in this relation is that distance doesn't appear in the formula. So how we conclude that here the electric field is independent of the distance. That's one way of putting it. Other way you could say that the electric field shall be uniform near the thin plane sheet of charge. Now is the time to consider two parallel sheets, you see. They might be similarly charged or oppositely charged. If they are similarly charged, means both are positive, then in that case, they'll produce equal and opposite field inside. Here it's going to be 0 within the two sheets. Outside they'll be added together. Here the field is going to be sigma upon epsilon naught, because when you'll add them sigma upon 2 epsilon naught 2 times, you are going to get this. If both are equal and opposite, in that case, outside the field will cancel each other by both the sheets, and within them the two field will add together to give the resultant sigma upon epsilon naught. Now its very important application is that for the plane conductor. If you consider a plane conductor having some thickness, whenever a conductor is given the charge, only the surface has the charge. The bulk has no charge. So what remains here is of no meaning. This is of no meaning inside. Only the two surfaces are going to have the charge, and obviously they'll behave as two thin similarly charged sheet. So for two thin similarly charged sheet, we have the field outside sigma upon epsilon naught. You can say near a plane conductor, the field is going to be sigma upon epsilon naught. Once you know what is the field near the plane conductor, suppose this is plane conductor, the field here would be sigma upon epsilon naught. You also know that the charge on the surface is going to be some finite value. Whenever the charge in the field is having some value, obviously it will experience some force, and some force will result in electrostatic pressure. We conclude that way, that whenever a sphere is charged, whenever a conductor is charged, it has the electrostatic pressure on its surface that's given by sigma square upon 2 epsilon naught. This concept of electrostatic pressure is very helpful in calculating the size of soap bubble, because there, in the case of soap bubble, surface tension is also causing its contraction, and at the same time this pressure, because of the charge, is going to create some repulsion. They will counter each other, and overall there will be still some pressure difference from that mass share.